over time, so probably I won't go over this example here, but the solution to this example is in the handouts I gave to you Friday last week. And also I upload the handouts to Blackboard, so you can download. If you wouldn't receive that email, you should receive. You can download from there. Okay, so that in this example I'm asking to calculate is so for this example, it's going to determine the response, and let me dig out that one. Where's my For this particular example with the solution I gave to you last time, the Friday, basically is based upon this equation, proceed to determine whatever the total response would be. Okay, so in that solution, you will see I highlight this form here. Okay, I highlight this form in the in the last step of that example, and then you can see that is a twice, should be twice. Okay. And if you would have any chance to read our textbook for the similar examples in these sections, I believe the liking of the factor 2. I don't think that is correct. Okay. So basically, I would say our textbook is to exercise simply for x only. Okay. So, but I think that must be specified, say the amplitude of the steady state solution. Then that would be good. That would be good. So that is the comments I want to make for this one. Any questions? No, and if no, then I'd like to give off this kind of exercise because I give you the handouts with solutions. I hope you can go over by yourself. And also you have gone over the exercise, the homework. And I look at most of people done pretty good. And so let me skip all those things. But if you still have a questions, you let me know. Okay. Today I want to start with the system with damping. So that means we're going to consider the similar situations by considering one more term, Cx dot. Okay, so we're going to consider damping. So with the additional terms, including damping, then we're going to go over the similar process. That means we will focus on how to get a particular solution or steady state response. And then we're going to have the similar analysis on the multiplication factors. Okay? And you could, at this moment, you should imagine these kind of factors will contain the parameters zeta, damping ratio. Okay? So for different damping ratio, they have a different curve, and the curve looks similar, but they would have many. And then in the final step, we're going to study the total response, and for these particular situations here. So that is the whole kind of the outline for these sections. So in a similar way, let's start over from here. We consider the damping components here. So that means the only thing different from what we have learned is we have additional term here. Okay, we have additional damping. So if you have gone through the homework and doing the exercise, I don't think by adding additional term will give us any, I would say, new things. No, basically the mathematics will be the same, but a little bit more rigorous by including the influence of this term only. All the steps are the same. Okay, so keep this in mind. Then we still consider the harmonic excitations. That means the force will be with the magnitude in sinusoidal oscillations. That will be either in cosine or in sine. Okay, and in our textbook, we demonstrated it is using cosine because using sine we simply is the 90 degrees ahead or behind, but that is really doesn't matter. Okay, so here I would try is in the lecture notes and follow up our textbook and using cosine as the for demonstrations, and if possible I will parallel to line up the sine, the calculation for sine and for comparisons. Okay, so before we're doing that one, and again, the total response composed of two parts. One is the transient response, okay, and the transient response, the same thing as way before, and that is determined by the natural frequencies, the oscillating at the frequency of omega n. Omega n simply is equal to square root of k divided by n. Okay, that is equal to an undamped vibration system, the vibrations, undamped natural frequencies, okay. And for the particular solutions, right now, the difference is this. Okay, so let me go over here. So right now we consider it is the damped vibration systems. So what we have is, let me say the space mx double dot plus cx plus kx and equal to f now cosine omega t. Or let me use color to indicate, or we substitute f now times sine omega t. So in this one, I try to use color to distinguish the calculations corresponding to the either type of the force. Okay. So for this case, we have particular solutions. Bless you. And earlier we take the assumed solutions. Okay, so here the homogeneous solutions, the transient solution simply is given by this, and that is from our previous chapters, right? Okay, so here if you remember x of t, and what is that one? That one simply is determined by the contents of the characteristic roots, right? If you remember, the characteristic root is this. The root we can express in terms of the damping ratio minus omega n t plus minus and omega n j 1 minus zeta squared, right? So here is our real part, and this is our imagined part, right? So either you express in terms of combination sine cosine, or otherwise, I prefer is this form is e. This is an exponential decay, and then multiplied with cosine and oscillating at the frequency that is the imagined part. And plus or minus certain phase angle. Okay, and then we multiply with the certain amplitude. Okay, so let me call the amplitude capital X here. Okay, and this one, if you want to explain it, you can also use in that form C1 cosine. I think I made a mistake there, so that should be omega dt plus C2 sine omega d. So this is omega d. Right? So let me correct this one now. I made a mistake here. Omega d. Okay, so sorry, my mistake here. Okay, so that is our contents from the previous chapters, and everything is the same. And right now we notice, and we have two unknowns, C1, C2, or this one and this one. Right? So now for particular solutions or transient solutions as our steady state solution. Again, the steady state solutions its role is to follow up perpetually the form of the external excitations. And our external excitation right now, either for this form, that is in cosine. So eventually it will follow up the pattern of the cosine. And that is what we learned from the previous sections. When we do the undamped system, if you remember, we assume the particular solution or steady state response in the same form. If for the previous sections, if we don't have any damping, if you can turn your notes a few pages earlier, if we have a cosine, then we simply, particular solution is in cosine. That's it. If this form is in sine, then our particular solution is in sine. That is for undamped, right? Okay. So right now, because we have a damping, the damping in mathematics, that is first derivative. Okay, because due to the addition of first derivative term, so for cosine, this cosine after the derivative, that's going to produce sine. So that means for any mathematics, if we have the first order derivative, in terms of physics, it's going to cause, it's kind of called the phase lagging or the phase leading. That means for this case, it's 90 degrees. Okay, so that means due to these reasons, due to the addition of the damping, not only we assume the final form is in cosine, but also we must consider the possible excitations of the signal due to including of this one, we also must consider sine. Okay, so combination of the two possible forms, that will make our guess complete. We won't miss anything. Will be okay? Okay, so that means really it doesn't matter this one or this one, we simply assume A1 plus A2. That's it. Okay, that one will make the things complete. We won't miss any important dynamic information. Will be okay? Okay, good. So right now we have this, and then we can proceed for okay, so that is the whole picture, and the remaining, we go to the next slide. And here is a summary of the results. So for the remaining, because we already have done from the chapter 2 about this form, so we've done this form, that is our final information. Okay, so we don't consider furthermore. So here in chapter 3, we're going to dedicate to this one. So in particular, we want to know what will be the A1, A2, or in particular, we can have another similar form like this. So that means capital X times, for example, we can say cosine omega t minus v, we simply put into this form. So here we have two unknowns, A1, A2. In terms of this form, we have two unknowns, capital X and v. And again, the capital X and V can be related to A1, A2 in terms of, for example, A1 squared plus A2 squared equal to X. Okay, and then for V, we have, say, arctangent something, I forgot. So, but that is kind of scratch, it's not important. Follow-up is we're going to adopt this form. We're going to adopt this form as for our discussions. And in particular here, I have give you the final result, and later I'm going to show you the process why the results are like this. Okay, so for example, the capital X simply equal to this number here. You first look at this number here. Basically, again, I'm going to show you the process how to reach this result. But before doing that kind of rigorous things, I think this is more important for us, for you to do the homework or do the exercise, because you're going to base upon the result and just proceed. Right? let's look at this one. So basically, the capital X is a function of those numbers, and F now. What is F now? F now is the magnitude of the applied loading. Okay. And what is K? K is our spring of the system. What is M? That is the mass. And what is omega? Omega is the working frequencies. And what is C? C is the damping constant. Okay, so among those kind of the long expressions, we can classify into two parts. The first part is from the system itself, which means K, M, and C. Good. The second portion is from the applied external excitation. That means from F naught, that's the magnitude of the harmonic excitations. From omega, that is the working frequencies. Again, the working frequency, like I mentioned to you, that is the parameters usually designed by engineers. You can choose. For example, you can choose omega to, say, have a system approaching to resonance, or you can choose omega such that the system has the minimum, say, amplitude or whatever the reasons. So basically, omega is the number you can choose. Okay. So that's the information. Again, for the phase angle phi, if we take this form, the phi will be arctangent. Again, that is determined by the system's parameters C, K, and M, and also determined by the excitation, that is omega. Okay. And on the other side, if we introduce, say, to get this term, we simply divide numerator and denominator by K. Okay, and later I'm going to show you why we get this one. But simply, this is the identical form of this one. This is called the static diffraction. Okay, and by definition, this one is defined by F now divided by K. Okay, that is our static diffraction, the same as we used before. Okay, and again, R is the ratio of the frequencies. So that is omega divided by omega n. So basically here we have the similar form. And the remaining, after we know this, the remaining process will be to get familiar with the curve, learn how to use the result, and then to use the result, the best way is, I think, looking graphically. That means looking at the magnification factors. Okay. So let me spend maybe a few minutes and on the blackboard to show you how to get the two forms here. Okay, so let me start from here. We can start from here. Okay, and then we can take because right now we assume this is the assumed solution, and this is a complete gas. A complete gas, that means we wouldn't miss anything. Okay, so now we're going to introduce into the governing equations. So introduce and into, say, let me call it equation 1, okay? So for this one, because here we assume the x, we need to know the first derivative and double dot. So here we just do this one. So for this one is A1 omega sine omega t minus plus A2 omega cosine omega t. Okay, and then xp double dot will be equal to minus a1 omega square cosine omega t minus a2 omega square sine omega t. Okay. And then in a similar way, I'm going to multiply, because here when we plug into the equation 1 each individual terms multiply with the certain coefficient. So that means this term will multiply with k, and this term will multiply with c, and this term will multiply with n, and then we take the summations, right? Okay, so my note has been written so concisely, and but when that time I was very focused, but not, now I'm multitasking, so a little bit gap, but I can do it. Okay, so we can do it here. So I think for this one we simply collect the terms and associate it with cosine or sine. Okay, so that means if the take summations, then we would have the term with the cosine omega t and multiply with something here, plus the terms multiply with the sine omega t. Okay, so those summations I'm going to collect into this form. So for cosine, then you need to help me. So that one, we cosine, we have this form here. So A1 A1k and cosine and plus A2c omega and cosine minus A1 m omega squared, right? And then for sine, then we have A2k, and for sine here, minus A1c omega, and for last term, minus A2 and omega squared. So that's it. Are we okay? Okay, and now this one's summation is altogether will be equal to this or this. So let me say this one will be equal to F now cosine omega t. And right now let me use color, or F now sine omega t. Okay, so from this step onward, I'm going to split my scratch calculation into two parts. One associated with cosine or with sine. Okay. So let me turn off this one for a while. I'm going to use the space there. Okay, so now we simply compare the coefficients. So right now, let me say the left-hand side equal to that form. So we compare the coefficient of the cosine and sine. We know that A1, let me do this, it will be easier. So this one, this form will be equal to F now. So that means A1 k minus n omega squared plus A2 times c omega equal to F now. Okay, right now I'm comparing is to associate with this form. Okay? And then for this one, this is a coefficient of sine. And when under that, the cosine, this one will be A2 K minus N omega minus A1 C omega equal to 0, right? You know what I'm saying? Okay, so now for this case, right now I want to compare the coefficients. If the harmonic excitation is in this form, then the comparison of the coefficient, again, this is the, this term must be equal to 0. And this term must be equal to F now. Okay?
Yeah.
I hope everyone follow me. Good? So now we simply need to solve for A1 and A2, then we done the deal. Okay, so with this one, then we can say for this case, so let me solve for the black one first. Okay, so for black one, let me do the scratch. So let me call the equation, let me from here. Okay, so from here for the black one, then I can say finding the A1 is equal to A2 and C omega K minus N omega squared, right? So when I deal with this set, and from here I get the A1, so plug into the first one here, so that means the A1 K minus N omega squared and C omega, this is A1, and multiply with this one, plus okay? So again, right now I'm using the second equation to find the relation between A1 and A2, and then I plug into the first equation, and I come to this form. You good? Okay, then we can solve for A2. A2 equal to okay, so therefore A1 equal to K minus N omega squared times A2. Okay?
Sorry?
Yes.
For when you're solving for A2, should the K minus M omega squared term be squared?
Yes. Perfect. Thank you. Thank you for the catch up. I think that is perfect, right? Okay, so yes? Okay. You good?
I don't think that should be squared. Yeah.
This should be squared as well.
But when you multiply A2, back when you're solving for A1, you have a K minus M squared on the top, right?
Let me do this carefully. A1 equal to C omega K minus N omega squared times A2. this one will be equal to A minus N omega squared plus C omega squared. And so that should be K minus N omega squared times F naught. So, okay, so that should be A1. Okay. And A2 from here, can I do this? I want to have A1 and A2 have the same denominators. So why not for A2 here? If you like, you can write one more, but here, let me take advantage of the whiteboard. I simply multiply the denominator and numerator with C omega. So that means this is C omega, and then this comes away, this is squared. That okay? Good? Okay. Not easy. We can separate. Okay, so let us focus on the black one. Later we can redo for the blue one. Okay, so right now for this one, so here we have is xp A1 cosine omega t plus A2 sine omega t, and I want to form into capital X and cosine omega t minus t. Okay, if I want to form this, get this format, and right now the capital X will be equal to A1 squared plus A2 squared. Okay, and I always forgot, so here let me do this cross calculation. If I expanded this one, this is cosine omega t cosine phi plus capital X sine omega t sine phi. Okay, so if I expand the cosine, cosine A minus B equal to cosine A cosine B plus sine A sine B. I simply use that equations to expand this one because I want to know what is phi. Okay, so from here you can see compared to this is cosine omega, so that means A1 equal to this. Okay, this is sine omega, so therefore A2 equal to this one. Right? So we have such relations. So from these relations, then we can obtain one is this, and also from here we compare tangents phi equal to cosine phi, sine phi, and cosine phi equal to A1. This is A2. Okay, so that is our tangents A2 over A1. Okay, and that should be in this way. So we plug in all the informations here. So therefore, we plug in informations square root of A1 squared and A2 squared. Jeez. Okay, so we just do it. A1 squared, A2 squared. I think that's it. Okay, help me double check because you have a bit of widened viewpoint than I am. Okay, so this one we simplify this carefully. So basically, the first one F naught, they both have a F naught square. So after the square root, can take out the F now. So let me kind of highlight the terms we're kind of working on, okay? And then they both have the same denominators, and that's a square term. So basically we can take out the denominators out, so that will be equal to this one. Okay, so right now I'm taking out all those circled terms. Okay, okay, and then remaining in the square root are the denominators c omega squared plus k minus n omega squared squared. Yes?
Did you accidentally put a squared on the CW?
Where?
Lower. Right there.
Here?
Yeah. It's supposed to be CW quantity squared.
Oh,
CO.
holy cow, yes. Thank you. Thanks. Yes. Are we okay? It's also good? If we are working on numbers, that'll be much easier. The same process. Okay. But here we work in the symbolic, a lot of writings. So right now you can see we can do one more simplification, then get our result. You can see basically compared to this square term with the denominators, can you see the denominator simply is the squares of this term? So we can cancel one term. So basically, again, let me take advantage of we can cancel this one. So basically the denominator becomes this one. You good? And probably you can write one more step and liken this. And so this one is appeared in our slides. So let me copy that information to here. So capital X from here is F now, and K minus N omega squared plus C omega squared. Okay, so let me copy that one, and later we can pull out the spring and look at one more time. Yes.
Need one more square on that quantity, the first quantity.
Yes, I always, yeah. Thank you. Okay, so again, we can have the similar way. If you don't mind, I leave the A2, A1. Okay, we can do it. I want to. So let me do that here. So the phi equal to arctangent A2 over A1. Right now we have A2 over A1. So that means A2 equal to this and divided by A1. So that simply is C omega and K minus N omega squared. That's it. If you compare to what we have this one here. Okay, so we can see. So that is our calculations, and here and here. So basically that is the same as we have here. Okay, and with those things in mind, let me work on the blue one, or if you like, you can work on the blue one by your own, but I can tell you, if you're going to work on the blue one, then the corresponding A1, A2 is here. A1, the blue one, that means when the excitation is in this form, okay? Then let me give you directly the result. The A1 will be equal to minus C omega. And A2 has the same denominators, and K minus N omega squared times F0. Okay. then under this case, the corresponding capital X for blue one will be the same. Okay, so if you conduct the sum of the square terms, take the square root, that will be the same as this one. Okay, the phase angle corresponding to blue one, you can imagine that will be 90 degrees apart. Okay, so for that one, the capital X is equal to the black one we have there. Okay, and for the phase angle, and that is C omega minus C omega K minus M omega squared. So I'm running out of this space. For blue one, corresponding to sine, the magnitude the same. The phase angle here is a minus of we calculated. Basically, that's 90 degrees apart. Okay, and this is an exercise, and in our textbook we demonstrated is using the black one. That means we demonstrated it's corresponding to cosine. And usually in vibrations, the phase angle difference we call the phase lag or phase leading, and that won't change the steady state response. The phase lag or phase leading simply is this. If you kind of watching the train passing by, right? So if they're moving at a constant speed, and each, how to say, train car, okay, they pass by, and then you simply wait for, say, a few seconds, or then you will get to see another appearance of the train car coming through. So basically that can be phase, okay, the similar, but they won't change the amplitude, the response, in particular the magnitude, okay. So with these things in mind, the remaining we will be focusing more is on the how to categorize the capital X. Okay, that will be our focus. And as far as the phase angle, that won't have too much. We simply just plug in for calculations. Okay, so keep everything in mind. Then remaining, I'm going to show one more derivation to how to get this one. So for this one, what we would do is this. We simply divide numerator by k and denominator by k. We simply divide the both sides by k, and we see what happens here. So from here, basically f now divided by k. That is our definition of the delta st. If you forget, delta st is called the static diffractions, and that's defined by the magnitude of the force by the spring constant of the system. That's the definitions. And now we work on this one. So we see k minus n omega square plus c omega square, and this one divided by k. We see what happens. Okay. So if this divided by k, then basically is that, again, I'm going to take advantage of the blackboard. So simply that is we divide the square root, the inside, by k squared, right? Okay, so then we can proceed. And then that simply is equal to, we have two terms. The first term divided by k squared, so that means k minus n omega squared, and this one divided by k. I simply get this division k squared into this term like this, plus c omega divided by k. Okay? Like this. And then this one you can see basically this one equal to 1 minus omega squared and k over n. Okay, so the first term k divided by k become 1. The second term I make arrangement like this. And the second term is C something like this one. I keep that one here. So k over n, basically this one is our omega n squared. Okay, and what is this one? So again, from our starting point, cx dot plus kx equal to f naught cosine omega t. And let me do this. So from here we can see 2 zeta omega n equal to c over m, right? And so from here, also omega n k over m equal to omega n squared. So here I want to make up the c over k. I simply divide this equation by this equation side by side. So again, from here, I want to get the information of c over k is what here we need. And I observe if I divide the 2 equations side by side, this one will be appearing c over k. This side will be equal to, okay? Can you follow me? Good. Okay, so plug in here. So that will be equal to 2 zeta omega n. So right now we introduce the R by definitions is the ratio of the frequencies. So from here you can see this term basically become 1R squared plus 2 zeta R squared, like this one. Okay, so that is what we have here. The denominator is the form here, and the numerator is delta st, just like we have here. And I can tell you, I've been never able to, even for teaching so many times, and then trust me, I studied harder than you. Because even I know the topic before I came to start the teaching, I still spend time to go over my lecture notes. So I go over again and again. Given those experiences, I've never been able to memorize these equations. But this one is good for me. Kind of give you my experience, okay? Because this one has more meaning than we had before. If you put the zeta equal to 0 with no damping, then this term will be simplified to what we've seen before in the previous sections. Exactly. Okay. So again, you can do it in a similar way for this. So coming back Wednesday, we will start from here, and we will quickly to look at the characteristic curve and then do more examples. And one more homework is available on Blackboard. Again, this one is due on Sunday, the end of the day Sunday. Again, the topic is to exactly for the damped vibration. That's it. And I just try to get everyone on the same page, kind of move on. Okay? Thank you.